Okay, so as I had, we started to go over on Monday, running through, we talked about the 1000 series. They're basically pure aluminum. The only important 3000 series, which are the manganese alloys, is 3003, which is used as sheet for production of beer cans, and 3003 has the unique property that you get very high ductility in the cold work condition, which makes it ideal for deep drawing applications. 4000 series, basically the only thing we care about is welding wire and brazing alloys, right? And the reason why 4000 series is very useful for these applications is the silicon gives us a lower melting point, right? There's a fairly deep eutectic there, but it doesn't give us a lot of brittleness. It doesn't reduce our toughness too much. 5000 series alloy with magnesium. Remember, we do get age hardening out of the magnesium, but these are typically used in the solid solution strengthened state because of the low degree of hardening and the very low solvus temperature of GP zones in magnesium. The critical issue is the formation of the beta phase, right, which nucleates heterogeneously, typically on grain boundaries and slip bands, and this causes a huge problem for stress corrosion cracking. And I talked about how the Navy is very keen on trying to find a way around this grain boundary sensitization problem, because they use these alloys for a lot of different applications and marine environments, right? You've got the perfect recipe for corrosion, and then extended times in tropical locations. You have ambient temperatures hot enough that you get grain boundary sensitization over the extended service life, right? You know, our Navy is not building new battleships or new destroyers every couple years, right? They stay in service a long, long time. Okay, they tend to age soften at room temperature, so we have typically work these in what's called an H3 temper, right? Which is where you cold work to a higher strength than you want, and then you do a short anneal at a slightly elevated temperature to exhaust softening, and this is known as stabilization, right? So big structural things, truck bodies, pressure vessels, container, ship containers, right, are basically what where these are used. Okay, heat treatable alloys, right? So heat treatable, remember, are those that we take advantage of age hardening, and these are the 2000 series aluminum copper, 6000 aluminum magnesium silicon, 7000 aluminum zinc, and I really should put the 8000 aluminum lithium alloys there. So the compositions that we're interested in are here, right? Notice that we tend to run from about 2% to 6%, maybe a little higher. Copper in the 2000 series, silicon we're generally less than to about 1%, with about the same amount of magnesium. We tend to keep those pretty balanced so that the overall composition is about 1.2 to 1.5%. of silicon and magnesium, and then 7,000 series with mag and zinc. We've got the ranges here where we're higher in zinc than we are in magnesium. Right, so just keep an observation here that I don't remember if I made during the age hardening. What's the crystal structure of magnesium and zinc? HCP, right? And we'll also see that in some alloys we add zirconium as we come up, which is also HCP, right? So different crystal structure we tend not to have the larger degree of solubility, right? That helps us with our high curvature of the solvus, and we will precipitate these out more, right? And these are just sort of a couple important alloys that are highlighted in terms of strength and properties, right? So if we take a look here, notice that the 7,000 series tend to be stronger than the 6,000 and the 2,000, right? And the our elongations are not, we don't have a huge amount. I mean, we've got sufficient ductility for applications, but it's not really extensive, right? Okay. So 2000 series, we talked a lot about the aluminum copper binary, right? Basically, the entire age hardening part of this was the aluminum copper binary, but we never actually use it, right? It's sort of like a nice case study, right? Because we can show the precipitation sequence, GP zones, theta double prime, theta, in a nice, clear way, right? Things happen in sort of a disjointed manner. We get these nice plateaus in our age hardening curve, but they don't make for particularly great alloys, right? Aluminum copper by itself will corrode in any application, right? A lot of these 2000 series alloys in practice are used as clad, right? So they'll be sheet and they'll actually clad a thin layer of pure aluminum over top, right, to help with the corrosion. A couple of the ones that are used sort of in the binary state is 2011, right, which has about 5.5% copper, but it also has lead and bismuth added to it. Those lead and bismuth will completely phase separate, right? So you've got a matrix of aluminum with these little tiny soft particles in it, and that gives you a alloy that has a very good machining properties, right? Has anyone ever tried to machine aluminum? Right? It's gummy, right? You get a horrible surface finish. You get these incredibly, if you're turning it on a lathe, you get these incredibly long chips that don't break and they wrap around things, and it's a horrible mess to work with. 2011, right, gets you these beautiful fine chips. It's like you're machining cast iron. It's self-lubricating, right? So if you have to mechanically machine something, 2011 is a good bet. Other than that, it doesn't really have any real commercial application. But we just call it the free machining alloy. 2219. This is useful because we have very high toughness at cryogenic temps, and so it's it's weldable, right? So this has some specialty applications for like liquefied gas storage in space vehicles, right? It's cold in space. Right? We need something that retains retains high toughness. It can be extruded, and typically it's used in a combination of strained, hardened, and then and aged in the T8 temper. Okay. So the general class of aluminum copper alloys was discovered completely by accident. Most of our alloys were, right? There was a great time of exploration. Let's just make a whole bunch of stuff and see what happens, right? The first stainless steels were invented by someone making what they thought was a failed alloy because it wasn't as strong as they wanted. And a couple years later, notice when they were cleaning out their scrap bin, those samples didn't rust while all the other ones did, right? Completely by accident. This was basically the same sort of thing by Alfred Wilm, 1906, and the first high-strength aluminum alloy was duralumin, right? Everyone knows this is one of the key allomantic metals if you're a fan of the Mistborn series, right? It allows the Mistborn to burn off their other metals in one big fell swoop and gives a lot of power. And I'll stop with the Sanderson stuff there. But this was really the first aerospace alloy, right? Used for Zeppelins, right? And a modified version of this is still used, 2017, for rivets. So basically, if someone has a small aircraft, a Cessna, right, that are aluminum wings, all of the rivets on there are 2017, right? They're mil spec. I forget the exact number, but good high strength. They can still be bucked at room temperature. They don't need to be stored. The next generation after that of important aluminum alloys was completely based on duralumin, right? So 2014 and 2024, right? 2014 gives us, you add a little more silicon in there, so you get a better response to artificial aging because you get GP zones of both copper and silicon, right? Yeah.
Are all these T8s just to stabilize the recrystallization?
T8 is just additional work hardening, right, on top of the, right? So T8, so oh, wait, it's in this one. All right, so T8, you get mechanical stretching after right? So you solution heat treat, quench, cold work, and then artificial aging, right? So T85 is 5% cold work, right? If you have two additions, two after, right? So 3, so T851, which comes up means it's the T8 temper, but plus then there's an additional stress relieving after it.
They do that just because once you precipitate your second phase, you have some extent hardening from plastic deformation.
You mean the rationale for the T8?
Yeah.
Well, it's just to leverage both hardening mechanisms, right? Right. So you generally in the T8 you'll cold work before the T8, or when we get to other ones where you've got T8 and then 2 numbers after it. That's because when you quench it, you get a lot of residual stress, and by doing plastic deformation after, you relieve those the stresses. Remember, residual stresses are elastic, caused by the thermal mismatch, and when you deform it plastically, right, you're applying a load over top of it, right, and you're causing plastic deformation and removing some of those residual stresses, right? So T2024, which is a really popular aerospace alloy, starting at around the time of World War II, we raise the magnesium and reduce the silicon, right? This allows us, we get more significant hardening at natural aging at room temperature, right? Rivets made of 2024 are called icebox rivets. They have to be shipped on dry ice, right? Because then you buck them in their soft condition, and then they will harden in place, right, and give you additional strength as they sit, right? If they warm up and come to their full temper, then it's completely impossible to actually use them as rivets, right? They won't deform on the backside, right? So this is basically, if you look at things like commercial aircraft, right? All those rivets are basically 2024 major fasteners, and shipping containers, right? There was a big case where shipping containers were basically ripping open when they were lifted by a crane, and that was because there was a couple years ago some counterfeit rivets. They were actually a 2017 like alloy rather than the 2024 that was put into place. So counterfeit parts are a huge issue, especially like parts with fake SAE stamp numbers or fake mil spec. There's a lot of unscrupulous people out there. Okay, so aluminum, copper, mag alloys, they still fall under the general classification of 2000 series alloys, but I won't go through any details just yet. So in general, right, if we look at the two classes, the 2000 series alloys will generally have a lower toughness than 7000 series, right? And this is due to the larger intermetallics that tend to form in 2000 series. We can, again, make improvements by reducing the iron and silicon. Iron, you'll see, keeps coming up as a huge problem, right? So we try to take care of that by making some modified alloys. 2124, right? Notice it's quite similar to 2024, right? So basically it tells you what it's related to. The iron and silicon are reduced, right? Quite substantially, right? And 2048, we are also quite lower. And if we look at these compared to 2024, so here we see we've reduced the iron and silicon by about half, right? Our strength doesn't change, but we can get very large increases in the fracture toughness, right? So if we look at 2048 versus 2024, we get very large gains and we approach what we get for the 7000 series. Right, with of course 7000 being much more expensive than 2000. Okay, so another benefit of the 2000 besides cost is that while the toughness generally tends to be lower, our fatigue properties tend to be slightly better, right? We have slower growth rates, right? So, right, this is the rate of growth per cycle, right, for a given stress concentration, right? And you can see we can go to for the particularly in the T3 condition, this bottom line here, right? We can go to significantly higher concentrations, or equivalently for the same stress level, we'll have a significantly slower crack rate once the crack is actually there. Okay. Important application is stress corrosion cracking, right? Which is the sort of the linchpin of all of our aluminum alloys. So what this here is, this is the crack velocity, right? And again, this is the stress intensity down here. And notice the plateau is about the same, right? So how do we interpret this plateau? Right. If we raise the stress, right, our crack isn't growing any faster, right? It's sort of like the steady state crack growth that no matter how high we make the stress intensity or K value, our crack growth stays basically the same, right? So that means we can sort of rank these by their effectiveness to stress corrosion cracking by just ranking their the K1 value for stress corrosion cracking, right? And so basically we see back here the older alloys 2014, 2024 perform sort of back here. The newer generation alloys 2048, right? Significantly higher K1s for stress corrosion cracking, right? Now keep this picture in mind because the 7000 series alloys look quite different, right? When we get to that, right? But the sort of the important thing to remember here is that right, everything sort of plateaus at the same place, right? So it really it really becomes a matter of what the stress intensity is rather than the long time growth behavior. Okay, so it's sort of embarrassing to say that when I say very advanced applications, right, and we talk about the Concorde, right, the Concorde hasn't flown in 10 years now, right, but it's still, in terms of aluminum wrought alloys, still really a very advanced application. So remember our age hardening curves for a lot of these, for a lot of these alloys, right? What would happen to most aluminum copper alloys if we were to age for 50,000 hours at 120 C? Right? How long would we remain in our high strength condition? Right? If you think about the binary, after about 100 hours at these sorts of temperatures, we're completely overaged, right? We're way down the backside of that curve. So we need something that has a high amount of stability at relatively elevated temperatures. Why did the Concorde need this and not other commercial aircraft? It was supersonic, right? Right? So very different conditions, right? So very different aeroelastic conditions, right? Basically have all kinds of fun shock physics, right? When you think about transitioning from subsonic to supersonic in the transonic regime, you've got a lot of buffeting, a lot more crazy sorts of flow. So basically, the alloy that was developed was 2618, which was on this previous chart here, right? 2618 is here, right? So not as good in terms of stress corrosion as 2048, but not so much of a big deal because, aircraft like this are constantly inspected, right? We don't need to worry so much about corrosion getting out of hand, right? Something that is taken care of on a very, very regular basis. So the basis for this alloy was actually a casting alloy, which was slightly modified, right? You can see we've got a soup here of all the usual players: aluminum, copper, magnesium, zinc, silicon, iron, right? And some nickel, right? Some titanium, right? Titanium, right? You could really take the titanium out and substitute zirconium in, and you'd have something very similar, both group four metals, right? And so this is kind of cool because we've got copper and magnesium present to affect age hardening, right? Nickel and iron give us a whole bunch of useful intermetallics, right? Happens that we get a lot of intermetallics that are particularly thermally stable, right? So they don't coarsen at these temperatures, right? Then we get silicon, which gives us additional hardening from GP zones, and helps with the distribution, a more homogeneous distribution of the stabilizing particles. Again, as you're going through this, I don't expect anyone to remember these details, right? Right. So don't try and memorize these, right? This gave us all of these precipitates in here, and the distribution gives us really nice creep properties, right? And so I sort of want to point this out, right? This is a huge mess. We'll keep seeing alloys that look like this in all of the systems, right? There's no way you could possibly predict from basic general physical principles how to create something like this, right? It's impossible, right? This is a huge amount of effort and experimentation, right? We can get some general guiding principles, right? So if you have enough experience, you say, okay, copper, mag, silicon, right? Okay, we know we sort of want these. We want to we need something thermally stable. We need things that create nice intermetallics. Let's try some nickel and iron, right? But beyond that, there's not a whole lot you have as a starting point, right? Yeah.
I thought nickel and iron, we were trying to eliminate that in 2006 now. It's for ductility and things like that.
Yep. So it's a trade-off, right? We're trying to balance. In this case, we need something that's going to be thermally stable and not lose our strength over time, and that's also good in creep, right? And we have to be willing to accept a trade-off in toughness,
Why is it good in cleat?
Just because you've got a large number of particles to pin dislocations at fairly low stress values. Right? All of these design choices are trade-offs. Right? What are the properties that you want to maximize? Right? What are you able to tolerate in your design? Yeah. Well, we'll get to the cast alloys. Well, generally, so the wrought alloys are anything that's going to be thermomechanically processed, right? So all of these that we basically have been talking about. The cast alloys are primarily silicon alloys and other stuff that is used in the basically as solidified case, right? We're gonna cast it, and so we take advantage of the solidification microstructures for our properties. Process thermomechanically, alloys that you're going to use in the thermomechanically processed condition rather than in the as cast condition. Right? Okay, so that's the 2000 series. 6000 series is probably what most people are familiar with, right? A lot of people have aluminum bicycle frames, right? Right, so 6000 is used in a huge range of basically consumer products, right? It's a sort of a medium strength structural alloy, and it's typically used as an extruded product, right? So we can make channels and tubes very easily. And the important thing is good weldability, right? So that means we can make things like aluminum scaffold, bicycle frames, right? Welded car body parts, right? And the main thing that we want to keep here is that magnesium and silicon are the main alloying elements, and we want to keep them balanced to form Mg2Si, and some alloys have a slight excess of silicon. And so we have three main types, right? So we have a balanced amount of mag and silicon. When I say balance, I mean stoichiometric amount, right? To give us a total alloy composition of about 0.8 to 1.2%, right? This is easily extruded and then immediately quenched, all right? And we can eliminate the need to have a separate solution heat treatment after, right? Because of the processing, the extrusion step. So the most right. So the quenching here, the extrusion takes the place of the solution heat treatment. Then we quench at exit. Right, we're extruding at elevated temperatures. Right, and then we will age these at between 160 and 190 C. 6063 is the most common alloy, right? And this is just used for a wide range of consumer products, right? Any sort of extruded channel, right? Decorative shelving, right? Window frame, right? A whole bunch of different stuff. The high purity version of this is 6463 with very low iron. Has really good anodizing properties, right? You can get a whole bunch of different colors. You ever see basically those anodized aluminum water bottles, right? Those are 6063, right? Used to be used quite a bit for automotive trim, decorative stuff. Okay, so if we raise the alloy and contribution, right, we have a slightly higher strength, but the trade-off is then we have to do a separate solution, heat treat and quench. We don't use it directly in the as extruded state, right? Contain again fairly, their mag and silicon are still balanced, and the most important alloy here is 6061, which is the bicycle frame alloy, right? And basically used this as a structural material. The third class is we raise things up a little bit more, and then we also has a little bit higher silicon, right? And again, we use these in after a separate solution, heat treat and quench, and the excess silicon helps us get a finer dispersion of these Mg2Si particles, which are our primary strengthening, right? But we have so we get higher strength, but again, the trade-off here is loss of ductility, right? And this extra silicon, while it helps us get a finer, more homogeneous precipitate structure, has a tendency to segregate to the grain boundaries, right? And can give us a significant embrittlement issue there. So we tend to add chromium and manganese and other fine stuff, other stuff to sort of counteract this, right? Right. I mean, this is again the alloy game, right? We add some magic pixie dust to do something. It does what we want, but then it does other bad things, right? So then we have to add more different pixie dust to try and counteract the bad things that the new one does, right? And that's how you end up with alloys with 15 elements added, right? It's the dog, chasing its own tail in some sense, right? And so there's often an unusual heat treatment associated with these. There's basically a quench and then hold at room temperature for a while before the aging step, right? And the idea here is you can get some clustering, vacancy and solute clustering, so that we modify the dispersion of secondary phase particles, right? Because things are going to tend to nucleate where these clusters are, and doing this is very dependent on the composition, right? So sometimes if we're under 0.9 mag silicon with a slight excess of silicon, it's good. If we're higher than that, then with an excess of silicon, it's not. Okay. So 6,000, we're rapidly moving through here onto the 7,000 series. Right. So this is aluminum zinc mag, and I apologize. This is sort of boring material, right? There's no way around it, right? It's sort of just this data dump. But again, I want you to have this sort of for reference, right? This is the part that will be least represented on the exam, right? Because there's not a lot of interesting things to talk about, right? I can give examples, right? I can ask a question, but give you some information and talk about it with respect to the previous lectures, right? But it'll be primarily on what's happening based on the strengthening and the age hardening part. Yeah.
So I've heard that 7,000 series are pretty bad in corrosion. Are they worse or better than 2,000 series?
I honestly Don't know that off the top of my head. They're pretty bad. 2000 pretty bad too. But I can ask Professor Locke or Professor Frankel. Right. Professor Locke, who she used to work at Alcoa doing stress corrosion cracking stuff, so she'd definitely be able to tell me. Okay, so 7000 series aluminum zinc mag, right? 2 hexagonals, right? They often have fairly small carbon, copper, not carbon, additions as well. Okay, so the ternary based alloys, right? Again, these tend to be medium strength alloys, very weldable. 7005 used to also be another very popular bicycle frame alloy, right? But is not so much anymore. 7005 used to be used because it was stronger than 6061, so you could get lighter bicycle frames. But with the advent of carbon fiber and titanium frames, that advantage has basically gone away. So for the same cost, you can have something even lighter weight, right? So which means that you don't see 7000 series used and used for those applications anymore, right? The ternaries harden at room temperature, right? And again, now I'm going to say something confusing, right? Remember, we talked about vacancies and GP zone formation. I talked about how cooling rate was really critical because if you cooled too slowly, you had a chance to anneal out your vacancies, right, and make it that much harder for GP zones to form, right? Here, these ones tend to be largely unaffected by cooling rate, so which implies that we're less critical, right? Our hardening properties are less critical on GP zone formation, right? So it's easier to nucleate and grow a more homogeneous distribution of the other particles, the other intermediate phases. In there, right? The key important things to remember about these are after welding, right? Remember, if you're welding, you've got a large heat-affected zone where we could be dissolving precipitates. We get a fairly significant recovery of strength recovering after welding, right? So at room temperature, the heat-affected zone will re-age, right? And we can recover a lot of our strength, right? This used to be, this is aircraft fuselage being built, I think. Or is that a train? Anyway, large structural transportation things, right, is where these come in. Again, big problem with stress corrosion cracking, particular in weld regions, right? While we will age in the weld region and recover a lot of the strength, you still do get a lot of segregation to grain boundaries that can give you issues with stress corrosion. Okay. Sort of an academic point, there is a optimal magnesium to zinc ratio, right? Where you get the max stress corrosion resistance, right? It happens to be at about when you have almost 3 times as much zinc as magnesium, with the total zinc plus mag being less than 6%, right? But again, the interesting thing is when we look at the alloys that we actually use, none of them fall into this optimal ratio for other reasons, right? So a lot of these we have to go through a modified heat treatment, slower quench rate, air cooling, basically. This minimizes our residual stress, right? We also, because we're not nucleating so many things or segregating, right? Basically, we reduce our internal electrode potential differences between all the little particles in there. So we have slightly better corrosion, right? And then typically then this will be artificially aged, right? So the aluminum zinc ternaries are good because they're weldable, right? Once you start throwing copper in there, we lose the weldability, right? So we can generally separate out the 7000 series into medium strength weldable, high strength weldable, and then high strength non-weldable alloys, right? Okay, so the ternaries are sort of these medium strength. Once we go into aluminum, zinc, mag, copper, this becomes quite complicated, and each alloy responds sort of differently. But this system gives us, out of all of the age hardening systems, the greatest response, right? The greatest delta from the quenched to the aged condition. These were found around the same time as duralumin. Duralumin was what, 1913? This is 1917, right? Significantly higher strength than the aluminum copper systems. The problem was corrosion, stress corrosion cracking. Right? So we saw here duralumin 420 MPa ultimate tensile strength, right? 580 MPa ultimate tensile strength. That's a huge delta, right? That's a huge difference. So there must be some really good reason why these were not used for all the aerospace applications instead of the 2000 series alloys that were developed, right? And this really was that of corrosion, stress corrosion cracking, right? So I guess historically the answer to your question is yes, they're worse, but I don't know about current generations of where they sit. So this issue of trying to solve the stress corrosion cracking, right? We have development of the long development cycle of things like 775, right? And, look at the soup, right? So very complicated. We can make, at the same time, people were working towards even stronger alloys, right? We get up to 610 MPa in the T6 condition for 7178, but the trade-off is we make our corrosion properties even worse, right? It's always the trade-off. Okay. So residual stress and the corrosion cracking issue led to a need to change processing conditions, right? So typically all the other alloys, cold water quench after the solution heat treatment, right? We want to quench as fast as possible to lock in our supersaturation of vacancies, right? However, this gives us very large residual stresses, and sometimes you would basically get quench cracks. You can't really see them here, right? Quench cracks and then stress corrosion cracks that would form due to the residual stress. And so part of solutionist was to basically use a boiling water quench rather than a cold water quench. But the biggest change was the development of a duplex heat treatment, which resulted in something that's called the T73 temperature, or T73 temper. And the rationale for this is pretty straightforward, right? Single aging step, right, at 120 to 135, which is sort of where we saw the optimal was for a lot of different alloys, right? We get a hardening curve that looks like this, right? After, this is up to 24 hours, right? So fairly high strengths, around 480, right? But bad stress corrosion. If we aged at a higher temperature, 160 to 170, we get a hardening curve that looks like this, right? Not nearly as strong, but a much better resistance to stress corrosion cracking, right? This fine dispersion of eta prime or eta particles, right? So the idea was a duplex heat treatment. So we age at first at 120, right? Cool down, and then bring it back up to 160, right? And this allows the GP zones to nucleate here, right? And then the fine dispersion of the eta and eta prime to nucleate on the GP zone, and we can recover much of our strength with an increased resistance to stress corrosion cracking, right? And this was used to great effect in very large forgings for the DC10 for alloy 7075, this T73 temper, right? And see, back the DC10 was out of service by the time most of you were born, but it was a triple engine with the third engine being in the tail, right? And basically, this is the forging, right? This is the engine mount, right? The spar for the tail section, and this was a single forging made out of this 775 with this T73 temper, right? And it was basically the only way we could make these at this time. Okay, so Friday we're going to go through the cast alloys, right? We should finish that up, and then Monday will be a review day. Wednesday I'll do a introduction to steel because no one will be paying attention because everyone will be thinking about the exam on Friday. Ben will be doing a help session, right? He'll be sending out a Carmen message to get that set up.